All right. What is the point estimate for the true mean? What do you think we mean by the point estimate for the true mean? The mean that they got. What was the mean that they got? 11.192. Absolutely. 11.192, and we say this is X bar. Remember, P is for proportions, for percentages. X bar is for sample means. So P hat is for sample percentages, sample proportions. X bar is for sample means. What would the population be? All Oreos. Fantastic. So what's the sample then? The 30 selected Oreos, absolutely. I'm going to kind of move around this counterclockwise. So we did population, we did sample. What's the statistic? Absolutely correct. X bar equals 11.1921. That is our statistic. That is what was actually collected when they did this little sample. What do you think the parameter would be? Super close. Do you guys remember how we had P for the true proportion and P hat for the sample? So we use X bar for the sample mean. Does anybody remember what we use for a true population mean? Mu. There we go. Mu is the true mean weight of all Oreos. I'm really impressed with how much you guys have remembered. So, fun little fact, Nabisco advertises the mean weight as 11.3 grams. Do we have some evidence that that might not be the true mean weight? Why? Because our point estimate was lower, so we have some evidence. We don't yet have any kind of convincing evidence, but we have some evidence that the true mean weight might be lower than what Nabisco is advertising. So they're gypping us on Oreos, making them slightly smaller. Was this sample a random sample? Yes. Why is that important? So that we can generalize the population, absolutely. We want to generalize our conclusion to all Oreos. That, if you remember from what we've done in the last two chapters, is condition number one that we always have to check. Is it random? What is the formula for calculating the standard deviation of a sampling distribution of X bar? Yes. Sigma of X bar, sigma is what we use for standard deviation, is equal to sigma. This sigma, by the way, just to be super, super clear, this is the population standard deviation. Anytime we see sigma, that's the population standard deviation. If we're going to use a formula for standard deviation, what condition has to be met? 10% condition, our independence condition. Has it been met? Yes. How do we know? There's at least 300 Oreos. Absolutely. There's more than 300 Oreos just at Kroger right now. So we have definitely sampled less than 10% of the total population. That is condition number two. Condition number one, was it random? Condition number two is our independence, or 10%. In the formula for standard deviation, this one right up here, number 4, we don't know the population standard deviation. Nabisco has not told us what the standard deviation is for all Oreos. So if we don't know the value of sigma, we're going to use Sx instead. If we did know the true value of sigma, then we would know the true value of mu, and we wouldn't need to do any kind of tests or intervals or anything. So this is what we have to do instead. The standard error, remember, we're not actually finding standard deviation because I don't know the population standard deviation. But I can find the standard error for x bar by taking the standard deviation of our sample and dividing it by the square root of n. If you look back up in that box up at the top of the page, does it give us the sample standard deviation? Yes, what is that? 0.0817, and then n was what? 30. So I want you guys to take 0.0817 and divide it by the square root of 30. Tell me what you get. 0.0149. I love it. So we've met condition number 1. We have a random sample of all Oreos. Means we're going to be able to generalize to all Oreos. We've met condition number 2, independence, our 10% condition. That means that we can use the formula for standard deviation, or in this case, standard error, because I don't know the standard deviation of the population. Would it be appropriate to use a normal distribution to model the sampling distribution of x bar? Yes. Now for the kicker. Why is it okay? Yes. How many did we sample again? 30. Central limit theorem applies here. We need samples of at least 30 in order for central limit theorem to apply. Why aren't we doing n times p, n times 1 minus p?
We don't have p.
We don't have p. There's no proportion, no percentages. So we have to come up with another way of checking to see if it's normal. One of those ways is if we have at least 30 in our sample. That is condition number 3. So we've checked random. We've checked independence, 10%. We've checked normality, large sample. I don't call it large counts this time because I'm not doing n times p. But I still want my sample to be sufficiently large. So at least 30. When finding the margin of error for a confidence interval, do you guys remember using z star? For a mean, we use t star. If you guys have one of these guys with you, the table A and the formula sheet and all that, go ahead and grab it out. If you don't have one with you right now or easily accessible, raise your hand. I'm going to get one to you right now. 3 over this way. All right, Ty, here's one for you. Okay, you see one? Who else needed one? Oh, I thought there was 3 in that group. Probably counted, sorry. Oh, no, it's just. Who else needed one? Okay. Anybody else need one of these guys? All right. So T star. I'm going to show you how to find T star in just a moment, but I want you guys to flip to the very last piece of paper. Kind of looks like the middle sheet. It's got this graph on it. Very last piece of paper in the packet. The shading, notice, goes the opposite direction, right? Yeah. They're shading now to the greater than side, whereas my z table shaded the other way. I don't know why they did that. The only thing that I can think of on this is that they wanted to make sure you didn't accidentally get it confused with a z-table. So they shaded it the other direction and they showed you the probabilities the other way. All right. Do you remember how to find z? How do you find z? Yep, absolutely correct. So to find t, we do pretty much the exact same thing. T is my sample mean, x bar, minus my population mean, mu, divided by the standard error, Sx over the square root of n. Oh, thank you. Okay, and I need to get you these two things. So here's the new homework and the new notes packet. We're on the first activity. So big question, why can't we just use z? So the reason that we can't just keep using z, we're estimating both the mean and the standard deviation. I don't know what the population mean is. I do know what my sample mean is. We're using that as an estimator for the population. But I also don't know the standard deviation of the population, so I'm having to estimate that also. We're introducing more variability because we're estimating not just one thing, but two things now. That means my graph is going to be more spread out. It's still going to have the same basic normal curve shape to it, but it's not going to have the exact same spread as a normal curve because we've introduced more variability now. There's an idea called degrees of freedom, and I'll explain what that means here in just one moment. But as my degrees of freedom goes up, my variability, or how spread out the graph is, also goes up. So I want to show you what these two graphs look like, a z-curve, a normal curve, compared to a t-curve. They are remarkably similar, but not the same. So the blue one there is my normal distribution with a mean of 0 and a standard deviation of 1. The red one is a t-distribution with 1 degree of freedom. What do you think the red graph would look like if there were 0 degrees of freedom?
Same.
It's going to look like my normal curve. As soon as we start introducing more variability, the graph gets more spread out, and then it still has that same basic bell shape to it, but it's no longer normal. What do you think the t-distribution would look like with, say, 10 degrees of freedom? It's going to have more variability, so how would that affect my graph? Would it be as tall? No, that peak is going to come down because where does that extra space go? It goes out to the side. So as it gets shorter this way, it gets wider this way. It still has an area of 1 under the curve. So if I'm spreading out here, it's got to come down.
Is there a limit on how many degrees of freedom we can have?
Technically, no. Technically, no. So if you're looking at that page that I asked you to flip to, look down the left-hand column. See how it says df? Starts at 1, it goes to infinity. And then across the bottom, do you see how it says 50%, 60%, 70%, 80%, 90%? And if you look right in the middle of that bottom row, it says confidence level C. So as we're doing confidence intervals, we're going to look at the bottom, and we're going to look at the degrees of freedom that we're using. And that's where our T star value comes from. So how many cookies were sampled again? 30, what we're going to use for degrees of freedom is n minus 1. So what would our degrees of freedom be? 29 degrees of freedom. So let's go find T star. So we're using what's called table B. That last piece of paper, our T distribution is table B. I want you to find 29 degrees of freedom. And we're going to do a 95% confidence interval. So 29 degrees of freedom and a 95% confidence interval. It tells us T star is what? 2.045. So now I want to calculate the margin of error. Does anybody remember how to calculate margin of error? Z star times standard error. In this case, we're going to do T star times our standard error. We're using a T star of 2.045. And what was our standard error again? .0149. There we go. Margin of error is T star times standard error. So 2.045 times 0.0149. So what is our margin of error then? .03047. Why don't we go ahead and round that to .03005? Is that okay? There's nothing wrong with keeping it .03047. Absolutely nothing wrong with keeping it there. So we're going to calculate this 95% confidence interval. So remember, the general formula for a confidence interval is point estimate plus or minus margin of error. What was our point estimate? 11.1921. And our margin of error is 0.0305. So I want you to minus that to get the lower bound and add that to get the upper bound.
Could you explain what the difference between margin of error and standard error is?
Yep. Standard error is the standard deviation of a sample. Margin of error is when you have basically normalized that. So you have to multiply it by your critical value. Yes. Mm-hmm. You're welcome. When somebody thinks they have an interval, let me know. Love it. I took mine out to 4 decimal places, although I don't usually. The only reason I took it out to 4 is because our sample data was out to 4 decimal places, but usually I would just take this out to 3 places. So yeah, I would normally have 11.162 to 11.223. How would we interpret that confidence interval? Does anybody remember how to do that from chapter 8?
Captures the true proportion of, so I mean the true mean weight of.
Yes, I love it. We are 95% confident that the interval from 11.1616 to 11.2226, and then I want to stick a little bit of context in here. How did they measure the Oreos in the sample? Grams. So I would stick grams in here so I'm getting some context in. So 11.1616 grams to 11.2226 grams captures the true mean weight of all Oreos. So I'm getting my context in there in 2 places. I'm going to pop this up a little bit higher on the screen. We want to write a specific formula for the confidence interval for a population mean. So I know it's point estimate plus or minus margin of error. What are we using for the point estimate here? X bar. So we have X bar plus or minus. How do we calculate the margin of error here? T star times what? Standard error, so SX, the sample standard deviation. SX is our sample standard deviation, divided by what? What do we need to divide by? Square root of n. So X bar plus or minus T star times the sample standard deviation, SX, divided by the square root of n. T is a different distribution. Normal distribution is called a Z. This is a similar but different distribution. So you know how we had our empirical rule, 68, 95, 99.7 for our normals? It would be a different rule for our T distribution because it is more spread out. It is wider and it is shorter.
And what is the X bar?
X bar is the sample mean. Sample mean. according to Nabisco, an Oreo weighs 11.3 grams. That is what Nabisco says is the average weight of Oreos, the true mean weight of Oreos. Do we now have, with our confidence interval, convincing evidence that that's not the case?
Yes.
Yes. Why? Yeah. The entire interval is below 11.3. What is the largest plausible value for the true mean weight? 11.2226. 11.3 grams is not contained in the interval. All the plausible values are less than 11.3 grams. Not tons, but think about how many packages of Oreos they produce. Do you think that skimping a little bit like that on each cookie would save them money? They definitely have an incentive to skimp just a little bit then. I found an interesting picture that I want to look at before we do the check your understanding. And it's actually catching a mistake that I made earlier, and I apologize because I'm still like in not quite fully healthy range, so my brain is a little bit addled. But this should clear it up. I will come right back to this screen, but I want to look for just a minute at this graph right here. See if I can make it small enough to show up completely on the screen. All right. Do you guys see all those bell-shaped curves? The green one starts down here, it goes up the highest and comes down. That's our normal curve, that's Z. The pink one right here, the lowest down one, that's a t-distribution with 1 degree of freedom. The blue one is a t-distribution with 2 degrees of freedom. The yellow one is a t-distribution with 10 degrees of freedom. And actually, if you look at table B, that very last piece of paper, I want you to look at this very bottom row that's actually inside the table. So right above where it has the confidence percentage, the confidence interval percentages, yep, where it says an infinite degrees of freedom, go look at 95% and an infinite degrees of freedom. Does that number look familiar at all?
Yeah.
What is that? That's a Z-star. So infinite degrees of freedom is our standard normal curve, our Z curve. As our degrees of freedom goes down, degrees of freedom goes up, it becomes more normal. Degrees of freedom goes down, it flattens out. So I misspoke earlier and I wrote it down the wrong way too, but I'll fix it on the notes. So as degrees of freedom goes up, basically as our sample size increases, because remember it's n minus 1, as my sample gets bigger and bigger, what happens to the overall curve? Does it become more or less normal? More normal. The larger the sample size is, the more normal it's going to be.
Is it possible to have
No, because it's always your sample n minus 1 for degrees of freedom here. All right, so now that I've cleared that up, and I will actually put this in the notes that are going up on Canvas so you guys have something to look at. And I'll fix it in my notes on here. All right, so let's go to the next page. Did anybody still need this? Okay. Heading over to the next page. Critical values. Z star is for P, for proportions. T star is for means. Degrees of freedom, n minus 1. You're going to use the degrees of freedom and the confidence level to find your T star. If you go to look up the degrees of freedom and it's not actually on there, because if you look further down, they start counting by tens at a certain point, you're going to round down. So like say if I had 94 degrees of freedom, I would round that down to 90. So if it's not on that left-hand column, then you're going to round down to the next closest number. Conditions, random, has to be a random sample, or if it's an experiment, random assignment. We have to meet our independence, our 10% condition. Normality, large sample. There are 3 ways we can meet this one this time. When we were doing proportions, there was 1 and 1 only. N times P, N times 1 minus P. Here, if it says the population distribution is approximately normal, we're good. You don't have to check anything. You just write down population approximately normal. If we don't have that, either that's not true or we don't know. If I have a sample size of at least 30, central limit theorem, and I get my normality again. If I have a sample that's smaller than 30, and I don't know about the population, or I know the population isn't normal, I can do like a dot plot on a number line with my sample data, and as long as it doesn't show any strong skews or outliers, I'm good. We can meet our normality, but you have to actually show the little sketch here. You can't just say sample data does not include any large skews or outliers. Sketch a quick little dot plot. This is all for stuff when you have less than 30. So your dot plot's not going to be huge. A lot of times there will be like a sample of 10 or a sample of 15. So you'll do a quick little dot plot on your page, see what that looks like. As long as there's no pieces that are way out or it doesn't have this strong skew, you get your normality. I want you guys to try to check your understanding. It's pretty quick today. We're going to check back in about 3 minutes. It's due on Monday. What is our T star for a 98% confidence interval and 26 observations? 2.485. 25 degrees of freedom and minus 1. 98%, so 2.485. What about a 99% confidence interval from a simple random sample of 85 observations? First of all, what's our degrees of freedom there? Technically it's 84, but what's the problem with 84?
It's not on the table.
Not on the table. So if I had technology that could actually do 84 degrees of freedom, that would be great. But I have table B to work with. So we have to round that down. We have to use 80. which would give us a T star of 2.639. Absolutely correct. Number 2, let's check conditions. On number 2, did we meet our randomness condition?
Yes.
How? Show me. Where?
They said they took a random sample of 1,640 adults.
Absolutely. Random sample of 1640 adults. We got random. What's my other condition? Or conditions? Independence, which is my 10% condition. Do you think we met the 10% condition? Yeah, there'd have to be at least how many adults? 16,400. It says a nationwide poll, so I said US adults. We're still super clear. There's at least 16,400 US adults. And then the last one we have is what? Normality, or large sample. This graph over here is the population distribution. Is it approximately normal? I want to know from the graph itself. The graph is not. So my population, super strongly skewed. It's not normal. Again, that's not my sample data. That's my population data. So I can't say population's approximately normal, I'm good. Do we get central limit theorem? Yes. So can we say it's approximately normal? Yes, we can. What's my third option? If I don't know about the population, or if I know it's not normal, and I have less than 30, what else could I do to still get my normality? Draw a dot plot. Draw a quick sketch. And what am I looking for on that sketch? No strong skew or outliers. So as I'm looking at that, a lot of times these dot plots of a small data set, you're going to have just one dot on each thing. As long as you don't have a group over here, and then one guy that's way over here, that would be an outlier. If you've got one that's a little bit farther away, that's not going to be a problem. Looking for strong skews and outliers. First homework assignment is due on Monday. As of right now, I'm planning on being here tomorrow. We will do the next activity in the packet. If not, you guys are going to have an assignment where you will go through the 4-step process for a confidence interval, which is what we were going to do in class anyway. And you will be allowed to work together if that's the case. All right? If for some reason I'm not here tomorrow, please be good to the sub.
We're always good to the sub.
Good.